looked up at the night sky or, even just watched something simple like a leaf falling and wondered, what if reality isn't quite as solid as it seems? What if the entire universe, everything in it, galaxies, stars, us, exists in multiple states at once, kind of like a quantum particle?
Right, until something observes it.
Exactly. It's a question that can really spin your mind into new dimensions, can it?
It definitely can, and it's a fantastic place to start.
And that really mind-bending idea is, well, it's right at the heart of today's deep dive. We're unpacking the groundbreaking theories of one researcher, Kevin Kandege.
Specifically, we're looking at two of his really profound frameworks.
That's right, Kandege's quantum universe and something called the coin theory.
And our insights today, they come straight from Kandege's papers. We've got excerpts from KandegeQuantumUniverse.pdf, and then two on the coin theory, one with stability analysis, one sort of laying out the basics.
So, our mission for you today is to cut through the, let's face it, potential complexity of these ideas. We want to pull out the most important nuggets, the key takeaways.
And really try to understand what they imply for how we see reality. From the biggest cosmic scales right down to the tiniest fundamental particles.
These are definitely cutting-edge concepts, and they can feel pretty dense. But we're going to try and offer you a shortcut, a way to get genuinely well-informed without hopefully feeling too overwhelmed.
Let's dive in.
Okay, let's start with that first big idea. Kandege's quantum universe. Most people listening have probably heard of the double slit experiment.
The classic.
Where a tiny particle, like an electron, it seems to exist as this fuzzy wave function, like a cloud of possibilities.
Until you measure it.
Right, and then bam, it sort of collapses into a definite location. Now, what if that exact same principle applied not just to a tiny particle, but to the entire cosmos?
Well, what's truly fascinating here is that Kandege's quantum universe proposes precisely that. The idea is the cosmos itself exists as a quantum wave function.
The whole thing?
The whole thing. In superposition, meaning it's simultaneously in multiple potential states. Like all possible universes existing at once until some kind of observation happens.
So it's taking quantum mechanics, that weirdness, and scaling it up to the absolute maximum level.
Exactly, to the ultimate scale.
And you said this isn't just like abstract philosophy, it's built on actual math.
Oh yeah, it's built on serious mathematical foundations. Kandege uses a form of the Schrödinger equation, which is, the foundational equation of quantum mechanics.
But for the universe?
But applied to the entire cosmos. It has to include everything, all forms of energy. Matter, radiation, dark energy, even gravity itself. It's all in there.
Wow. And I saw mention of the Wheeler-DeWitt equation, too. That sounds familiar, but intense.
Ah, yes.
Yeah.
That one pushes the boundaries even further. It's even more mind-bending because it actually removes time for the picture entirely.
Removes time.
Treats the universe as a timeless entity. It uses concepts from quantum gravity, things like the supermetric spatial curvature, the cosmological constant, essentially describing the universe's geometry at this fundamental, timeless level.
Okay, my brain is officially starting to melt, but here's where it really flips things, I think. This concept of a meta-observer. If the whole universe is a quantum wave function just waiting, something has to interact with it to make it, real. To cause that collapse. What exactly is this meta-observer?
Well, the meta-observer is basically whatever interacts with this universal wave function and forces it to pick a state, to collapse into a reality, the one we experience.
How does that work? Is it modeled?
Yeah, it's modeled mathematically.
Yeah.
You introduce an interaction term, and that causes the wave function to collapse into a specific outcome, collapsed.
Okay.
And this actually aligns pretty well with a concept called decoherence theory.
Ah, right. Where quantum systems lose their quantumness just by bumping into their environment.
Exactly. Decoherence explains how interaction causes that quantum fuzziness, the superposition, to vanish, and things start looking classical, like our everyday world. The meta-observer interaction is like decoherence on a cosmic scale.
So wait, observation isn't just passively looking at things, it actively shapes the reality we experience, even the whole cosmos.
That's the implication, yeah. It's a huge shift in perspective. It suggests reality isn't fixed. It's a dynamic interplay, a negotiation almost.
Between potential states.
Between all the possibilities, yeah. And observation is what collapses those possibilities into the concrete reality we live in.
Okay, that's big. Now, a lot of people listening will know about the many worlds interpretation, MWI.
Sure.
How does Kandege's cosmic wave function idea connect with many worlds? Does it support it or offer a new angle? And where does something like M theory, with all its dimensions, fit in?
Well, this framework actually offers strong support for many worlds. The idea is that every time a macro-scale quantum event happens, maybe even a conscious choice, maybe just a random interaction, the universal wave function branches.
So a new universe splits off.
Exactly. A distinct universe for each possible outcome. So yeah, every possibility you can imagine might genuinely be playing out in some of the branch.
In theory.
M theory, with its concept of higher dimensional branes or membranes, well, it could provide the spatial canvas for all these multiple universes. It suggests these different realities might exist parallel to each other in these higher dimensions.
And maybe the meta-observers interact across these dimensions.
That's a possibility explored in the framework, yes. That interactions could happen across these branes, influencing which reality, which branch gets actualized or experienced.
Okay, if our choices, our agency, might influence which branch of this multiverse we experience, that's huge. That's not just physics, that's philosophy, that's daily life. How far does Kandege take that implication?
It definitely raises some really important questions for all of us, doesn't it? I mean, if reality is this dynamic process where observation collapses possibilities,
Maybe what we do matters on a cosmic level.
well, it suggests human agency could potentially play a role. It might influence which branch of the multiverse, which set of possibilities we end up experiencing. It gives you a new and, pretty profound perspective on free will.
And just existence itself, really, within this vast landscape of probabilities.
Exactly. We might not just be inhabitants of reality, but active participants in its ongoing creation.
Wow. Okay, that's one absolutely fascinating side of Kandege's work, the quantum universe. But incredibly, he doesn't stop there. He proposes an entirely different way to look at reality.
Yet complementary, perhaps.
Right, with what he calls the coin theory. So instead of the universe being one giant wave function, this theory suggests space-time itself emerges from two interacting things.
That's right, the coin theory. It proposes that space-time, the very fabric of reality, isn't fundamental. It emerges from the interaction of two basic entities he calls time threads and space threads.
Okay, threads. What are these? Are they like strings in string theory?
Good question. Not exactly. Time threads are defined as vibrational energy carriers. Think of them as carrying the dynamic, energetic aspect.
Okay, energy carriers.
And space threads, as represent geometric curvature fields, like the shape aspect of space-time.
Got it.
But the key difference, and what sets this apart from string theory or loop quantum gravity, is how Kandege treats them. These aren't discrete, tiny strings or loops. No, they're modeled as continuous vibrational fields. Everything else, space, time, particles, forces, emerges from the interactions of vibrations of these underlying fields.
Okay, continuous fields. Now, one of the most, radical ideas in this coin theory is that things we think of as absolutely fundamental constants, like g, the gravitational constant, or c, the speed of light, they aren't actually fundamental at all.
Precisely.
They emerge from these threads. That just completely flips our understanding, doesn't it?
It really does. It implies the basic rules of the universe aren't fixed laws written in stone, but are actually dynamic properties arising from this deeper level.
How does that even work? Like, take E equals MC2. How does that come from threads?
In this theory, that famous mass-energy equivalence arises from vibrational standing waves formed by these threads. Mass energy isn't fundamental either. It's directly linked to the vibrational frequencies, FTNFs, of the time and space threads.
So energy is HTFT plus HSS, where HT and HS are thread constants.
Exactly. And mass is just that energy divided by c squared, which itself emerges. So mass comes from the vibrations. It's like finding out the chessboard isn't a fixed board, but it's alive and shimmering, and the rules emerge from that shimmer.
Okay, mass energy from vibrations, that's already pretty out there. But then you're saying constants, we always thought were truly bedrock fundamental like gravity itself. G also emerge. How?
That's the claim. Kandege derives the gravitational constant, g, directly from the properties of these threads. The formula proposed is g OKLH-TS 16C3.
Wow.
And through dimensional analysis, you can see how it works. The thread constants, HT and HS, have dimensions of energy times time and energy times length, respectively. When you combine those dimensions, along with the speed of light c, which also emerges, we'll get to that, you end up with the correct physical dimensions for the gravitational constant. It falls out of the thread properties.
That's quite something. And the speed of light, c, the ultimate speed limit, how does that emerge? It's not just assumed.
No, it's also derived. It comes from the balance of energy propagation between the time and space threads. The theory gives C2 equals H is HT.
So the ratio of the space thread constant to the time thread constant determines the speed of light?
Exactly. It suggests C isn't just some arbitrary universal speed limit, but it's a consequence of this deeper interplay between the energetic and geometric aspects of reality, represented by the threads.
And it suggests a whole deeper layer underneath what we thought was fundamental.
Definitely. Where even something seemingly fixed like C is actually a result of a more fundamental dynamic.
Now, a theory this bold, this different, it needs ways to be tested, right? Otherwise, it's just speculation. Does the coin theory offer any experimental predictions? Things we could actually look for?
It does, yes. Which is crucial. For instance, Kandege predicts a specific signature in high-energy particle collisions. Like in electron-positron collisions producing a photon and maybe a graviton, there'd be a specific cross-section related to these thread constants.
So a unique fingerprint we could potentially detect in experiments at places like the LHC if we look hard enough.
Potentially, yes. Something unique that standard physics wouldn't predict. Also, the theory predicts a very high-frequency cutoff for gravitational waves.
A cutoff, meaning gravitational waves can't have frequencies above a certain point.
Exactly. Around 125 hertz, according to the paper. That's extremely high frequency, but maybe, just maybe, future generations of gravitational wave detectors could probe that regime.
Interesting. Okay, so there are potential tests, but what about stability? Can these thread configurations actually form lasting structures? Can they make up the particles and objects we see around us?
That's addressed too. Stable mass configurations are proposed to emerge as what are called soliton solutions.
Solitons, like those weird waves that keep their shape?
Exactly like that. Think of them as incredibly stable, localized waves or knots in these thread fields. They maintain their shape and integrity, essentially acting like the building blocks of particles, without just dispersing like normal waves.
And that requires certain conditions.
Yes, for these soliton solutions to be stable, the theory requires a specific interaction parameter, lambda, to be positive, oscurely.
Okay. And I assume there's more work to be done here.
Oh, absolutely. The papers mention future work exploring cosmology based on these threads, looking at quantum fluctuations arising from them at the very smallest scales, and trying to build deeper links to thermodynamics, energy flow and entropy in the universe.
Right. So let's try and connect the dots here. We've explored this idea of a universe that's a giant quantum wave function where observation, maybe even our observation, collapses reality.
Kandege's quantum universe.
And then this other idea, the coin theory, where space-time itself and even fundamental constants emerge from underlying interacting threads.
Yeah, two very different pictures on the surface.
So how do these two profound frameworks, both from Kevin Kandege, connect? Do they complement each other for you? How do you see them fitting together, if at all?
Well, if we try to connect this to the bigger picture, I think what they both do, profoundly, is challenge our traditional views, our assumptions about what's fundamental.
Okay.
Both frameworks present a universe where things we thought were fixed, like constants, might actually be emergent, and where observation isn't just a passive measurement, but plays this incredibly active role in shaping what's real.
So they both point towards a more dynamic, less fixed reality?
Exactly. They offer a novel interpretation of reality itself. They invite us to think more deeply about things like macro-scale quantum effects, quantum weirdness applying to big things, maybe even the whole cosmos and just the fundamental nature of existence.
What really stands out to you about how these theories push the boundaries? I mean, it's a lot to wrap your head around, isn't it?
It really is. But what stands out for me is perhaps the sheer audacity, the elegance in trying to connect these huge, seemingly disparate ideas. From the weird probabilistic nature of quantum mechanics.
Right, the fuzziness.
All the way up to the fundamental constants that govern the entire cosmos. Trying to bring that all under a single or at least related conceptual umbrella.
It's ambitious.
Hugely ambitious. It's a powerful reminder of how far theoretical physics can stretch our imaginations. And it suggests that maybe, just maybe, the deepest truths about reality lie in seeing the interconnectedness of everything in ways we haven't fully grasped yet.
So let's bring it back to the listener. What does all this mean for you, listening right now?
Well, I think it leaves you with some pretty big questions to ponder. If our reality is potentially just one possibility collapsing out of a vast cosmic wave function.
Or if the constants we measure in experiments emerge from vibrating threads.
Right. What does that truly imply about the nature of those experiments, about the very structure of the universe we perceive? Does it change how we think about scientific truth?
What new questions does this provoke for you about the actual fabric of existence? And maybe even your own place within it all.
It's definitely food for thought.
Absolutely. We really encourage you to continue your own exploration, your own deep dive into these fascinating, mind-bending concepts, and maybe, just maybe, to question what you thought you know about the universe.